Say hi. Okay, so today we're moving on to volumes of revolution. You have a question first? Right. If it's horizontal, the outermost, the larger values would be to the right, and the smaller values would be to the left. So you're integrating still, I would say you're still integrating A to B. You're integrating from the smallest number to the largest number. You're integrating A to B in this direction, or you're integrating A to B in this direction. Okay. Yeah. Okay. So let's get back to volumes by revolution. So let's move, actually let's show the rectangles. There's our original rectangles. There's just one rectangle. Let's just revolve that. Now I want you to think about what 3D figure do we get when we revolve that rectangle. And notice here, this original area that we were talking about, this original area that's going to get rotated, that's sitting away from the axis of rotation. There's this space in here now. There's a space. So what happens when you revolve just this one rectangle even around this axis of rotation? Can you think of what that 3D figure looks like? A washer. Awesome. Okay, so a washer is just a disc with a hole in it. Okay, right here you're just going to have a hole. That's just empty space. All right. So now what we want to think about is how can we develop a formula to that we can use to compute that volume. So what we're going to do is think about taking the volume of the entire disk. Okay, so the volume of the entire disk would just be some pi r squared h. And then what if I subtract out the volume of the hole? That would be another pi r squared h. I took the volume of the entire thing and then take out the volume of the hole in the middle, subtract that away, I should be able to come up with the volume of what's left over, which is what I'm interested in. So that's what we're going to do. I'm going to clear this thing that I kind of messed things up with. There we go. So let's first look, I think what I will do is reset this so that we can look at this image. Here's our area that we're revolving. Here's our axis of rotation. And now what I want to do is find an integral that describes the whole thing, supposing that were a disk. So in that case, we would have volume equals pi times the integral. We would be integrating from A to B, according to this diagram. And then our radius is going to be this whole distance all the way down to here, okay? If this were a disk method, we would be assuming this rectangle would just stretch all the way down to the axis of rotation. So our radius is this y-coordinate here minus this y-coordinate here. Or if our rectangle is over here, the radius is this y-coordinate here minus this y-coordinate here. That's the distance, okay? That's your outer radius, and I'm going to call that big R of x, okay? That's like an outer radius. That's the outside radius. And then the inner radius is going to be the radius of the hole. So this radius we describe as whatever this y-coordinate is, which is f of x, and then minus this y-coordinate, which is -2. So the outer radius is f of x minus -2, and then the radius gets squared, and then we integrate with respect to x. Okay? So it's not quite as simple as it was before. You've got an outer radius that gets squared, and now the inside radius is this right here. Here's the inside radius. That's going to be, this time my f of x, everywhere along here, what's the y-coordinate? 0. So the inner radius, I'm going to call that little r of x, that is, that's for the other volume. So we have pi times the integral from A to B So if I set up this one, it's going to be 0 minus negative 2 squared, because that's the inner radius, this y-coordinate minus that y-coordinate. And whenever you're trying to name a distance in positive, as a positive number, take the bigger value and subtract the smaller. So 0 minus negative 2 gives you positive 2, and that's the distance there, 1, 2, you can just count it. Okay, so you have 2 squared, and then dx. Pi times the radius squared dx. Then we're going to take this volume and subtract this volume. Okay? Yeah?
Will they always give you the axis of revolution?
Oh yeah. Yeah, you'll always get the axis of revolution. So if I take this volume right here and subtract that volume right there, then I'm going to really get this. I'm going to put it all into one integral now. I'm going to put the pi out in front, and I'm going to integrate from A to B. And then, in this case, I have f of x minus 2 squared. And then I'm going to subtract this other integral. So that's going to be minus 0 minus negative 2. Actually, this should be minus. I needed a negative there. There we go. Squared dx. And so in terms of a formula, the way this usually looks, we'll write it as a formula. We're going to write v equals pi times the integral from A to B. And we'll write the outer radius, however you calculate that. If it's this function minus, however you calculate that, is the outer radius squared minus the inner radius squared. And then the whole thing integrated with respect to x. So we essentially put the two integrals together. We take outer radius squared minus the inner radius squared. That gives us the volume of the entire solid minus the volume of the whole. And that's what we're after. All right, so let's look at an example from the notes. Take out your graphing calculators if you would. So we're going to have to graph something here. Okay, so in this problem, what we want to do is we're going to find the volume of the solid of revolution generated when we revolve the area between the two functions f of x and g of x about the x-axis. So the first thing I want to do is to graph those. So enter those two equations in your graphing calculator, and let's just see what those look like, the graphs of those. We could certainly graph those by hand, but I don't want to get all bogged down with a bunch of graphing. I just want to solve this problem for today. Okay, so we have our graph. It looks like the graph crosses the x-axis over here at 1 and then over here at negative 3. You guys getting that? Something like that. And then it crosses the y-axis right here at positive 3. So that makes sense. We've got a line that goes right up through here like that. And then we've got this as our other curve. Okay, so it looks like you've got points of intersection at negative 3, at x equals negative 3, and at x equals 0. And you could certainly confirm that by just plugging those numbers into both equations and confirm that they have the same solution. So this is the area that I have. All this area between these two curves. It's this area that I want to rotate now around the x-axis. Okay? I'm going to rotate that area around the x-axis. And just like we did yesterday, we're going to draw our representative rectangle so that it is perpendicular to the axis of rotation. So here's our axis of rotation, the x-axis. Here's our representative rectangle. That is perpendicular to the axis of rotation. And now I just want to identify both an outer radius and an inner radius. The outer radius is always going to be from the top of the rectangle or from the furthest point away from the axis of rotation. So this is going to be your outer radius, big R of x. This is going to be your inner radius, little r of x. Okay? So if we rotate this whole thing, r of x, if we consider the solid that would be formed if we rotate r of x around the x-axis, we get the entire solid, and then we're going to carve out this intersection. Okay, so let's go to our formula, which is volume equals pi times integral from a to b, and we want to come up with a function for the outer radius, square that, come up with a function for the inner radius, square that, and then integrate with respect to x. So how would you name the outer radius for this example? Outer radius is going to be all this, right? Just our f of x. Okay? So when we plug that in, this is where it's going to get a little messy when you start to compute these. So our outer radius is negative x squared minus 2x plus 3. That gets squared. And then my inner radius is going to be whatever this y-coordinate is for the linear function. So the inner radius is going to be x plus 3 squared. Okay, and notice if we take this outer radius and then minus 0, it's just going to give us the function. And here is just the function height as well. So we didn't have to subtract anything like we did in the previous example. Okay, so all of that dx. Now, this is going to be a lot of computation if you do all this by hand, because first you have to square this trinomial, you have to square the binomial, add up your like terms, and then you're going to finally use the power rule. Okay? I'm going to suggest that we do a lot of these problems using your calculator. Less and less on the AP exam are they looking for you to grind out all of that algebra and then try to integrate without making any errors at all. So more likely what they will do is they'll probably, rather than have some kind of polynomial function, there will be some function that they give you that you can't integrate by hand, so you would have to use your calculator. Okay? So we want to integrate, we need to look at our limits of integration. It looks like these two curves intersect at -3 and at 0. So I'm going to go ahead and fill in those limits of integration, and then we'll talk about what we're going to do with the graphing calculator. All right, so at this point in your calculator, you probably have the function f in your y1, and you probably have the function g in your y2. So now we want to integrate this whole thing. So here's what I'm going to suggest you try to do. Go to your y3, and in y3, I want us to enter this. Okay? Now you can just type it all in if you like. That's perfectly fine. Just type it in straight across. Or if you want to enter it in using the vars notation that you find in your calculator, you can do vars, y vars function, and then choose y1. Vars, y vars function, choose y2. And then you can just square the y1 or square the y2. Whatever you have to do, you're going to put that into your calculator. So it's going to be like y1 squared minus y2 squared. And you can use the y variables, or you can just type the whole thing. I don't care how you do it. So now we want to integrate from -3 to 0. So at a minimum, our window on our calculator has to be open in the x direction from -3 to 0. notice when you graph y3, this is the function that we're actually integrating. Okay, we're integrating y3. It's not going to look anything like the two graphs y1 and y2. It's a completely different graph. So turn off your y1 and your y2 and just leave y3 on, and then integrate from -3 to 0. So second calc, option 7. And then tell me what you get for the integral part of it. 21.6 here. Did anyone else get that?
Yes.
Okay, so 21.6. All right, so that's what you get when you integrate it. And now you have to remember to multiply by pi. Did you have trouble, Karen? You're supposed to put y1 squared minus y2 squared. You got that? Now you graph it. And now you do second calc, option 7. That's your integral. Your lower limit is -3, your upper limit is 0. Integrating -3 to 0. All right, is anyone having problems with that? So the only thing that's different about washer method is you're actually kind of computing two volumes and subtracting them. All right, let's take a look for a few minutes at some of the homework problems from last night. So I'm going to pull up last night's solutions. And this is your opportunity to ask questions about anything from homework, 1 to 4, 7 to 10, 23, 28, any of those that you had trouble with. How many of you checked your answers? Awesome. How many of you got them all right? Awesome. Okay, how many need help with any of these before you take the quiz? Okay, I'll ask Number 8? Okay. We can look at any of these you guys like. I'm happy to go over any of them. So here's a couple, actually, here's a couple where we go around the y-axis instead of the x-axis. Let's take a look at that. Just kind of by comparison, number 4, we're rotating around the x-axis. So we're going to be sure to draw our representative rectangle perpendicular to the axis of rotation. See how that's perpendicular? And then whatever is the shorter end of the rectangle, if it's along the x-axis, then you're integrating with respect to x. If it's along the y direction, then you're integrating with respect to y. So in this problem, the function is written y as a function of x, so that's helpful. It's already written in terms of x. The dx is that little short part of your rectangle, and then we're integrating from 0 to 3. As opposed to problem number 7, where you have an area here, and if we rotate this area around the y-axis, like is shown here, now the only way you're going to cut cross sections that are discs is if we cut across this solid horizontally. Okay, so anytime you rotate around the y-axis with the disc method, your rectangle is going to be horizontal. The rectangle and the axis of rotation are always perpendicular. That's always a big hint. So if you have a horizontal rectangle, then we just have to set everything else up in terms of y. So we have pi times, we want the radius of this figure, depending on if you're here, or here, or here, or here. There's a radius, there's a radius, there's a radius, there's a radius. The radius is always whatever the x-coordinate is, and the x-coordinate is square root y. You have to write x as a function of y, because everything in your integral has to be in terms of y. So if the x-coordinate this time gives us our radius instead of the y-coordinate, then you're just going to put square root y in your integral. We have to square that by the formula because it's radius squared. And then your limits of integration are going to go in the y direction. So we go from 0 up to 4 for your limits of integration. Okay? Now, someone asked about number 8, did I hear that? Or no? You did? Okay. All right, so let's go to number 8. Okay, so here's another example, rotating around the y-axis. You've got this graph of root 16 minus x squared. So, they gave it to you y as a function of x. That makes it kind of easy to graph. But when we rotate around the y-axis, our axis of rotation is perpendicular to our representative rectangle, then again, you have to integrate with respect to y. So you have to rewrite the equation x as a function of y in order to integrate that way. So you're looking at this original equation, you're solving for x. Square both sides of the equation, that's how we get here. Solve for x squared by subtracting 16 and then multiplying through by a negative 1. And then finally you get x equals the square root of 16 minus y squared. So the x coordinate again is your radius. This is your radius, so that distance is whatever that x coordinate is. X is the square root of 16 minus y squared. So here's your radius squared. Multiply, you're going to integrate with respect to y. Pi is out front, and then your limits of integration are again along the y-axis, 0 to 4. Does that answer your question? Okay. Other questions about anything at all with disk method? Aubrey? Can you what? Sure. So here's 10. So these are y limits. So this is y goes from 1 to 4. Okay? Otherwise, yeah, that would be a problem, wouldn't it? Yeah. We're going to integrate from here to here in the y direction. Okay? Notice all of my work is worked out with fractions because typically, 4 or 5 years ago, we always had to, a lot of the AP exam problems would include this as part of the no calculator section, so you had to do all this work with tons of fractions and stuff. And it was a big mess because a lot of kids made mistakes on the fraction parts. But I'm really here to try to, improve all of your math skills, but definitely grade your calculus. So what you're going to do today for your quiz is just setting up the integrals, okay? So you're going to set up the integrals. You don't have to solve them. You don't have to integrate anything. If you want to use your calculator, you may, but the whole idea is really just to get the integrals set up correctly. So think about whether you're setting up an area or a volume.
Will it be clear saying volume?
Yeah, I'll give the directions. So tuck everything under your desks if you would.